Alright, so today I'm going to be explaining this important paper with the title DHAKR, Learning Deep Hierarchical Attention-Based Kernelized Representations for Graph Classification. This AAAI 2025 paper. Graph-based representation are a powerful tool for analyzing structured data. In this paper, we propose a novel model to learn deep hierarchical attention-based kernelized representation for graph classification. To this end, we commence by learning an assignment matrix to hierarchically map the substructure invariance into a set of composite invariants, resulting in hierarchical kernelized representation for graphs. We introduce feature channel attention mechanism to capture the independencies between different substructure invariants, and that will be converged into a composite invariance, addressing the shortcomings of discarding the importance of different substructures arising in most existing R convolution graph kernels. This is an example of the motivation that we have independent structures, and from that we create composite structures. For example, 1, 2, 3, 4 is just one structure. The other one is 2, 1, 4. But you can consider all of them into just one composite structure. So given two graphs GM and GN, we know the R convolution graph kernel can be written based on the similarity between the substructures. So based on different types of substructures, most R convolution kernels can be divided as kernels based on walks, paths, or subgraphs or subtrees. Given a pair of graphs GM and GN, the WLSK kernel is computed by counting the number of common subtree patterns, and this T sub max is maximum iteration number, and this L sub T of sub I is the I's node label of the iteration I. So C is counting the subtree pattern labeled by L sub T in G sub M. The idea is to compare the isomorphic shortest path within pairwise graphs. Given a pair of graphs, the SPGK kernel is written like this. So first we compute the feature vector for each graph based on specific R convolution kernel. Since WLSK and SPGK have more effective performance for graph classification, and their associated substructures have proven to be powerful structural characteristics of the original graph, we extract the shortest paths on WL-based subtrees for phi. Second, we hierarchically combine original substructures into more meaningful structures by adaptively computing the assignment matrix to hierarchically converge the homogeneous substructure invariance into composite substructure invariance. Third, during the above combination process, we employ the attention mechanism to discriminate the importance of different substructures for the substructure invariant converged. And finally, we compute the hierarchical kernel matrices. by concatenating the individual kernel matrices based on different hierarchical level composite substructure invariants. We employ the above concatenated kernel as a multi-scale kernel-based graph embedding. And so we have graphs with R convolution, we create these, but we create a substructure invariance, and then we get the feature attention because we have different kernels using, we can create also dense layers. And the construction of substructure invariants. We employ WLSK. As I said, there are just counting subtrees. And it's a edge hierarchical combination of substructures invariants to capture dependence and homogeneity between invariants. With the feature matrix X, we compute the soft cluster assignment matrix as S. So we can derive the feature matrix like this. During a hierarchical combination procedure, since the importance of each substructure is different, we introduce attention mechanism to facilitate feature selection, aiming to eliminate redundant substructural information unsuitable for graph classification. Inspired by channel attention, we employ average pooling. So with the attention scores, the feature matrix can be updated like this. This is just a feature-wise multiplication. Now here we create, based on the kernel matrix can be computed directly by dot product of pairwise feature vectors. So first we use average global pooling to extract aggregation information in the kernel. And different from feature attention of this here that we use the kernel-wise multiplication and summation for hierarchical kernel matrices from 0 to H, and update the H layer weighted kernel matrix. So the family of H hierarchical kernel matrices can be updated. We employ the kernel matrices as graph embedding representations. So we employ all sample graphs as prototype graphs and embed each graph into vectors using the kernel-based graph similarities. To introduce supervision signals to guide the model, we feed the family of H hierarchical kernel embeddings to dense layers of classification. We can derive the label prediction in the following way. So we have this cross-entropy loss for graph classification over all training graphs. Each substructure should be assigned to a specific cluster. For example, cluster assignment probability for each substructure should be close to a one-hot vector. We add this regulation loss for soft cluster assignment matrix. This is an instance of construction of H layer weighted kernel matrix. They did experiments on proteins, MUTAG, these graph classification benchmarks. And they compared this model, for example, DGCNN with DHAKL-WL. 3% improvement on MUTAG. AR is just the average rank. And this is the visualization of the hierarchical combination. This is the hierarchical composite feature visualization that you create these composite substructures